All right, you're welcome to class. This is PET 237, measurements and shapes. We are going to consider significant figures and uncertainty in measurements. We'll continue our teaching series. Let us explore in brief the idea of uncertainty in measurements. For example, if the volume of a liquid is measured using a graduated cylinder, where the result is 32.6 cm3, then 32, which is the first value of this measurement, is certain. The last digit, however, which is 6, is considered uncertain. If you tell anybody who is familiar with measurements that the volume of a liquid is 32.6 cm3, that person would understand that the last digit, which is 6, has some uncertainty in it. And that the volume of the liquid is probably somewhat between 32.5 cm3 and 32.7 cm3, of which if you observe it, you see that 32.6 cm3 lies in between 32.5 cm3 and 32.7 cm3. Now for this reason, that is why the last digit is often considered uncertain, because a lot of times it lies in between two other values. Alright, let's proceed. Basically, the last digit that has some element of uncertainty in it is called the least significant value or digit. It is least significant. In the above example of measured volume, the least significant digit is 6. It is obvious, which is the last digit. Of course, we can often refer to 32 as more significant. By convention, it would be incorrect to report the above measured volume as 32.60 cm3, as this would indicate that the uncertainty in the measured volume occurs in the last digit, which is 0. In other words, the volume is in between 32.59 cm3 and 36. So that means 32 also, not 36. There's an error here, so it has to be corrected. It lies between 32.59 cm3 and 32.61 cm3. That is where 32.60 cm3 lies. Alright? Now let's see how we count significant figures. In order to write significant figures correctly, it is important to understand how to count the numbers of significant figures or significant digits in a measured value. As you will see shortly, this is most important in working with significant figures in calculations. The value 32.6 has 3 significant figures, which you obtain simply by counting all the digits. However, some numbers contain zeros, and zeros are not always significant digits. In fact, they are not always often referred to as digits that are significant. For instance, let us consider the number 0.0326. The first zero is written to draw attention to the decimal points. So, of course, you see that this first zero may be considered as not being significant because it's just written to draw attention to the decimal point. It is not a significant figure, as I've rightly earlier said. This zero could be omitted, though it is preferable to include it. So when writing the first zero, when zero appears like that, it's always preferable or advisable to include it, though it's not significant, but it should be included. The zero to the right of the decimal point, that is the one after the decimal point, is also not a significant figure. The easiest way to understand this is to write the number in scientific notation. We've learned scientific notation in other units at the earlier aspect of this course. So go back and see how we write significant notations, which is writing this 0.0326 in scientific notation. We have, as I thought before, let me just throw a little light on it. The decimal point is here. We move it 1 and 2. We are moving from the left to right. So decimal point we relocate and find itself in between 3 and 2 rather. Therefore, we have 3.26 times 10 to the power minus 2. This is because we moved only twice from the left to right. When you move from left to right, there's always a negative power. When you are moving from right to left, the power becomes positive. So the main purpose of the 0 was to tell about the correct decimal magnitude of the number, the correct power of 10. The number 0.0326 has only 3 significant figures. So when you want to know the significant figures in digits, for instance, for the sake of example, if it is given to you, maybe several numbers are given to you and you are expected to find out how many significant figures it has, it is often advisable to write it in scientific notation like this, then before you know the number of significant figures present in it. Let's say, for example, let's assume we have 0.0056, and you are asked, how many significant figures does this digit have? Let me increase it so that we'll see it for clarity. How many significant figures are here? It's advisable to just convert this quickly to scientific notation, of which we are going to move the decimal point from where it is now to this point in between 5 and 7. And if you count it, it is going to be 3 movements: 1, 2, and 3. So we are moving 3 times. Therefore, our new decimal point will be in between 5 and 7 times 10 to power. We move 3 times. I move from left to right. Times 10 raised to power minus 3. Minus 3. Take it up that way, it becomes minus 3. Okay. So, the number of significant figures it has is 2. I'll come down and say it has 2 significant figures. So that is it. Just 5 and 7. They are the significant figures. Right? That's just a quick example. So this is just to show you how it's also counted. So the zeros, beginning zeros are not counted as significant figures, but the zeros after the numbers are often considered. What is the status of the 0 at the end of the measured number? Ordinarily, the end 0 is the least significant figure. It's also significant, but it is the least significant. Consider this now, 0.03260. We say it has, how many significant figures does it have? It has 4 significant figures, because the 0 here becomes significant because of these real numbers that appeared before the 0. So the numbers or the zeros before the numbers are not significant, but the zeros that appears after real numbers are often considered as significant. But the last 0 is often considered as the least significant figure, as we rightly earlier said. So this is just a recap of what I've explained before. So the rules for counting is very, very simple. Let us, to consider the rules for counting, let us take examples. Examples will make most of these things clearer to us. Alright? Example. Counting or count the number of significant figures in each of the given numbers. Count the number of significant figures in each of the given numbers. Alright? Let us see. A steel rod is measured and reported to be 11.0608 cm long. Don't forget what we are doing. We are counting the number of significant figures. So if you are asked now, how many significant figures does this one have? The solution here, count all digits including the zeros, because I told you that the zeros that appears in between or after a real number is considered significant. Therefore, we will say that this first one has 1, 2, 3, 4. It has 4 significant numbers. Option B, a computer reports the time it takes to calculate a class average at 3.160 seconds. How many significant figures does it have? As we have said before, the zero after numbers are significant. Therefore, we say that it has 4 significant figures. 1, 2, 3, and 4. It has 4 significant figures. So for the sake of exams, zeros that appear after real numbers are significant. But the ones that appear before real numbers are not significant. When the zeros appear in between real numbers, they are also considered as significant. Alright? Then option number C. The volume of solution in a bottle is found to be 2.90 ml. Right? So how many significant numbers are there? We have 3 significant numbers because we've said before that the zeros that appear after real numbers are also significant. Number D. The distance between 2 points is found to be 7,800 meters. So of course, how many significant figures do we have in option D? Option D, we are going to write this in standard form. Write standard form. Okay, let's do now. It is not clear how many. If any of the zeros are significant without more information, according to rule 3, you see it up there, rule 3. If the number has 3 significant figures, you could make this clear by writing it as 7.80 by 10 to the power 3 meters. So if the point now here is after the 0. So move 1, 2, 3. So 7.8 from the right to left, the power becomes positive, power of 10 is positive. So you count all digits in 7, this is the virtual error here, root 6, 47, 7.80 as significant. So the number of significant figures, these that are here in 7,800, they are 3 and not 4. Because most of us might be tempted to think also that since we have said before that zeros after real numbers are significant, we might just say 1, 2, 3, 4, which is wrong. So it's often best, since there's no decimal points anywhere here, it's often advised for you to convert or take it to scientific notation before you take your final decision. But when you take the scientific notation, you now see that what is being reflected here is, we said initially that zeros are just meant to point you or take you on the emphasis of where the point is, decimal points is located. So when we take decimal point from here now, 1, 2, 3. So what is going to be left there is going to be 7.80. You can't say 7.800. No, wrong. 7.80 by 10 to the power 3. So you can attempt this self-assessment on your own. How many significant figures are there in each of the following quantities? Take a look at this. 16.06 million. How many significant figures are there? 69.00. How many significant figures are there? How will you? I'll take this first and foremost to scientific notation. C, 30.200. Same thing applies here. Take the scientific notation, then you know the number of significant figures that appear. So, self-assessment 1, you are expected to do this and submit online. It will be graded. So, you are advised to do it and submit online. On page 26, self-assessment 1, A, B, and C. Do it and submit online. It will be graded. So, let's consider exact numbers. We have so far discussed measured numbers. In the next section, we will describe numbers that result from calculating with measured numbers. All of these numbers have some uncertainty associated with them. You would also encounter exact numbers which arise when one counts items or when one defines certain units. For example, the length of a desk is found to be 8 meters. It means exactly 8, not 7.9 or 8.1, because 7.9 is approximately 8, 8.1 is also approximately 8. But we are dealing with the exact number, which is 8. Right? And also, when it is said that there are 12 inches in a foot, it means exactly 12. No approximated values. Right? Significant figures in arithmetic results. When measurements have been made, the tendency might be to do calculations with them. For example, if you want to find the floor area of a room, you first measure the length and width of the room. Then you multiply the length by the width to find the area. Of the room. Alright, so if the length of the room is 7.5 and the width is found to be 8.5 meters. Given these measurements to two significant figures, both of them are these two significant figures, also two significant figures. We are saying that you know the first digits with certainty, but feel the second digit has some uncertainty in it. To find the area, you multiply the length by the width on your calculator. The calculator result is 62.75. Therefore, area is equals 7.5 times 8.5, and we're going to get 62.75 meter square. Meter square the unit for area. Right? Then you cannot write the answer as calculator result because of the uncertainty involved in the value. So, in the calculator's result, you may have several. Let us activate our calculator and see. We have several answers. Okay, let's say 7.5. 7.5 multiply it by 8.5. Let's see what we are going to have. Okay, we have the exact value of the statistical error here. It should be 63.75. So not 62.75. So there's also a statistical error in our module. So it should be 63.75. Alright, so 63.75 meter cube. It said you cannot write the answer as calculator result because of the uncertainty involved in the value. Okay? We'll throw more light on that subsequently as we go ahead. Generally, because measured values have uncertainties in them, the result of a calculation with the numbers has an uncertainty. This uncertainty is expressed by writing the results to the proper number of significant figures. There are rules guiding this decision. These are given in the next section of our discussion. Right? I think we have just 10 minutes left for this particular lesson series. Rules for significant figures in calculation. We can simply go through the rules. Those ones are straightforward. They are straightforward. They are straightforward. Okay. Okay. Yes, this the aspect I want us to really concentrate on, rounding off numbers. Rounding off numbers. So once we are abreast with this, because for the sake of exam, you must round numbers off. Rounding off numbers, we have to either round up or round down. And there are certain rules guiding it. Alright, I'll not bother you with just going through the reading. Let's just go through the rules. For the sake of time, you can go through that in the module. Rules for rounding of numbers. If the first digit to be dropped is less than 5, leave the preceding digit as it is. Rule 2. If the first digit to be dropped is 5 or greater, increase the preceding digit by 1. Look at the leftmost digit to be dropped. Let's consider example 3.2. Perform the following arithmetic and give the answer to the correct number of significant figures. Take a look at this. It said 14.942 plus 88.1. It's here already. (14.942) plus 88.1. Let's activate our calculator. A lot of times it gives us some typographical errors. So 14.942 plus 88.1. Our result is 103.042. So it's also correct from their own analysis. So 103.042 rounds to 103.0. Why did we end at 0 or at 0.0 here? Because take a look at the preceding number, which is 4. Before the 0. The preceding number is 4. 4 is not up to 5. And from rule 1, we say that if the first digit to be dropped, which is 4, we are dropping 4, is less than 5, leave the preceding digit as it is. So we are going to leave the preceding digit, which is 0. 0 is preceding 4. So we want to drop 4, and because 4 is not up to 5, we'll leave the preceding digit as it is. When you do something like this, we call it rounding down, because this 4 is not up to 5, so we round it down, call it 0. 0 plus the preceding 0 here will give us 0. So we have 103.8. The next one, if we do it, we have 8.16. We want to drop 6. We are dropping 6. 6 is up to 5 and more than 5. So what do? We round it up and call it 1. We add that 1 to this preceding 1 here. 1 plus 1 is 2. So instead of writing 8.16, we write 8.2 because we have done certain arithmetic rounding off here. Alright? So once the digit you want to drop 6. Then we'll ask ourselves, is the 6 up to 5? Is it up to 5 or more than 5? If the answer is yes, then we'll round it up and call it 1. Add it to the preceding value. Right? Take a look at this. We have 22.3125. So we want to, this is where we are ending here. We are rounding this up to 20 something. So we are dropping, the one that is underlined is what we want to drop. So for the sake of emphasis, okay? So we are dropping the preceding one, or the one after the underlined one rather. I think the one after the underlined one, that's what we are dropping. So 22.3125, we are dropping 3. What was underlined is 2. So we are dropping 3. 3 is not up to 5. It's less than 5. So we round it down. We call it 0. 0 plus 2 is also 2. So that is why we are dropping 3 down. So what we have left here is 22. We rounded 3 down because it's not up to 5. 3.5696. We are dropping 6 down. Alright? So we are retaining 5. Take a look at the number after 5 that is on the line here, which is 6. 6 is more than 5. It's up to 5 and more than 5. So round it up, call it 1, add it to this 5, it becomes 6. That's how we have 3.6. So I would like us to quickly go through this self-assessment to carry out the following arithmetic and report the answers to the correct number of significant figures. Alright? So carry out this operation and present your answers. Let me make it standard. For self-assessment 2, present all your answers to 3 significant figures. Oh no, that'll be too much. Yes, okay, let's use 3. Present all to 3 significant figures. 3 significant figures. Alright? Let me see how you're going to do that. So do self-assessment 2 and also submit. Submit online for grading, to be graded. So you have 2 work to submit online. Self-assessment 1 in page 26 and self-assessment 2 in page 29. So carry the operation out. You are going to leave all your answers in 3 significant figures, or to 3 significant figures. So in conclusion, it is evident from our discussion of this unit that variations do occur when measurements of the same quantity are taken. It has also been shown that these noticeable variations usually impose certain limitations on the result of measurements. In the final analysis, you were treated to why these uncertainties occur and the use of significant figures in reducing those limitations. So this is a summary of the lecture. You go through the summary, and we are going to stop here for now. Also go through the tutor math assignments from number 1 to 3. Go through it for your personal consumption. I'm not saying you should submit this one. You're not to submit the tutor math assignment, but just go through it for your personal consumption. Alright, so in our next lecture series, we are going to continue from Unit 4, which talks about unit conversion and calculations. Alright, we'll stop here for now. I'll see you again in class in our next lecture series. Alright, goodbye for now.